Okay, at this point we're studying the motion of objects that move in circular orbits or circles. So first a quick review of some of the basics that are going to be important. This is a great time to do this since this brings back a lot of the things we've done already, and those things are going to be part of our midterm exam. So first, the quantity fully described by magnitude alone is known as a scalar quantity. And if a quantity has both magnitude and direction, that's known as a vector quantity. So it's scalar and then vector. Speed, which is just a measure of how fast you're going, a number, is a scalar quantity, whereas velocity, v, is a vector quantity. It's both your speed and your direction. So again, it's scalar and vector, which turns out to be a. The equation for calculating average speed of any object is just speed is equal to the distance that you move, delta x, delta y, whatever, divided by the time period that takes. Okay, now the type of motion that we're studying moving in circles is uniform circular motion. So if it moves uniformly in a circle, it can have constant speed in that it's not getting faster or slower. The numerical part is not changing. But at the same time, it could have a changing velocity because as it moves round and round the circle, its direction is changing. So if you look at the top-down view of something that's moving around a circle, here's our object. Now, its velocity is tangent to the circle, touching it only one point, going in that direction. When I've gotten around to this point, the length of the arrow would not have changed, but the direction of the arrow would have changed. So the speed didn't change, our speed was constant, but the velocity, the direction, did change. The direction of a velocity vector is always the same as the direction the object is moving. So velocity vectors show you the direction you're moving. They do not show you the forces. They don't tell you anything about the forces, just your current state of motion. 6, true or false. The direction of the velocity vector of an object is at a given instant in time depends on whether the object is speeding up or slowing down. That's false. Okay, the acceleration will determine if it's speeding up or slowing down. The velocity vector, again, is simply going to point in the current direction, the direction that the object is currently moving. With circles, it's tricky because with every moment, you're going in a different direction. So your velocity is changing, but your speed may or may not. Now, if the object is moving in uniform circular motion, uniform in this case means the same, stays the same. The thing that's staying the same is the speed. So uniform circular motion means we're moving around the circle with a constant speed. Now the velocity vector will always be directed, in that case, as we go round and round the circle, here, or here, or here, or here. It's always touching the circle at one point, so it's always tangent in the direction of the tangent line drawn to the circle at the object's current location. So when it was moved here, its velocity vector would be tangent to the circle, touching only at one point. When it was here, it would be tangent to the circle. When it was here, it would be tangent to the circle. Now, throughout this motion, this object is moving counterclockwise, and again, it's like a top-down view. Use your average speed equation to determine the speed of. Now, keep in mind that around a circle, the circumference of a circle is 2 pi times the radius. Ride on a carousel ride that makes a complete revolution around the circle in 17.3 seconds. Now, again, to find velocity, the speed, we just need the change of distance over time. Now, as we go around a circle, that's actually going to be the change of the circumference over time, which means it's going to be 2 times pi times the radius. Now, they give us the diameter of 21.2, so we actually want to use the radius of 10.6. Now we could use pi times the diameter. That would also be fine. It would give us the same result. We divide that by the time, 17.3 seconds. That'll give us a speed of 0.363 meters for every second that we move. So not very fast. It's a old-fashioned carousel ride. It's a nice leisurely ride round and round as we move on the carousel. B, our clothes are plastered to the wall of a washing machine during the spin cycle. The walls make a complete revolution every 61.9 centimeter diameter circle in 0.285 seconds. So V is going to be equal to the circumference change over time. Once around is 2 pi times, well, let's just go pi times the diameter since we have the diameter. And we're going to turn that into meters, 0.619 meters divided by 100. Centi stands for 1/100th. And we're going to do that every 0.285 seconds. Which gets us to 6.82 meters for every second. Now notice we're going around a much smaller circle, but we're going we're making the turn in much less time. So 0.285 seconds, pretty quick turn. So we're moving pretty fast to make that happen. Finally, a roller coaster is traveling over the crest of a hill. Is the location shown. It's a side view hitting over top of the hill. We're going to use an arrow to show the velocity vector. Again, if we think of this arc as being a circle, then the velocity vector needs to be tangent. Now I'm going to assume it's going to the right. It's kind of hard. There's no real distinction to tell us. If it's moving to the right, then the velocity vector is going to be tangent to the circle, touching at only one point to the circle at that position. If it was moving to the left, then our velocity vector would look like this. Okay, so moving to the left it would be green, moving to the right it would be the red, but it would be tangent to the circle at that point. Okay, so that's our first episode of Moving in Circles.